Good morning, class. So last time we have seen the SAR for the adrenergic agents. So generally the SAR of adrenergic agents is classified into two parts. That is the SAR regarding the adrenergic agents which having the phenylethylamine in their structure, and second one imidazoline ring in their structure. So last time we have seen the SAR of adrenergic agents which having the phenylethylamine in their structure. Okay, so this is the some summary part of the SAR part for the phenylethylamine. So this is the structure of phenylethylamine. So this is the phenyl ring, this is the ethyl ring, and this is the amine. So that is the basic ring which present in the sum of the adrenergic agents. That is the phenylethylamine. Okay, so we will just go briefly to what we have seen in the last lecture. That is the SAR regarding the phenylethylamine. So regarding the nucleus. So the three important parts which is required for the activity. First one is phenylethylamine. Second one, this is the catechol ring which consists of the two hydroxy group, and third one, this hydroxy group which is present at the first carbon, or which is present on the first carbon. So these are the essential parts, or these are the required parts for the optimum activity of adrenergic agents. So the drug which consists of phenylethylamine in their structure. So we will go one by one. What are the SAR part? So here we can see in case of this R1 part, if we increase the size of R1, it becomes more beta active compound. So if it is methyl, it having the alpha activity. But when we are increasing the size of that alkyl part, that is the ethyl, propyl, butyl, so it will increase as the beta receptor activity, and the alpha receptor activity decreases. Hence, we increase the size of R1, then it increases the beta activity and it will decreases the alpha activity. So another the benefit of this is that if we increases the size of R1, so it will degrade, or it decreases the degradation by the monoamine oxidase. So it is difficult for the enzyme monoamine oxidase to cause the oxidation of this part. So if we increase the size of R1, it will increase the beta activity and it will decrease the alpha activity. If we made it that a tertiary butyl, so if methyl is there, they will show alpha activity. But if ethyl, propyl, butyl, it will show the beta activity. And if the tertiary butyl group is there in R1, then it shows the beta 2 activity, or it is selective for the beta 2 receptor. For example, colterol they have given. So colterol is the more beta 2 active as compared to the other drugs. Okay, if beyond that, if we increase the size of R1, that is the pentyl, hexyl, heptyl, then it will the drug becomes the alpha blocker instead of a agonist activity. So in case of labetalol or the drug, you can find out that that drug they having the large R1 part, and due to the having the large R1 part, the drug becomes more antagonist instead of becoming agonist part. So that is the part regarding this R1. Then second one regarding the R2, which is present on the alpha carbon. So if this R2 is small substitution like methyl, it having the increase alpha 2 activity. But if we increase again the size, it is the ethyl, propyl, then the beta activity increases and the alpha activity decreases. It will also affect the metabolism by the monoamine oxidase. So it decreases the degradation by the monoamine oxidase. Okay. Now important part regarding this basic nucleus. So in that basic nucleus, there is a catechol. It requires two hydroxy groups. If two hydroxy groups are there, drug becomes agonist for alpha as well as the beta receptor. But what the main disadvantage is that due to the hydroxy group or the catechol nucleus, they can be undergo easily the metabolism by the enzyme catecholomethyl transferase. So we have to make some modification to decrease its metabolism, so that if this one of the hydroxyl group, we will move to the fifth position, then the drug becomes 3-5-dihydroxy group. At that time, it will increases the beta 2 receptor activity. Or if one of the group we convert it into the CH2OH instead of hydroxy group, then also it will increases the beta 2 activity. So these are the modifications. If we have do, we can go for the beta 2 receptor activity. Here you can find out if 4 hydroxy group, only the 4 hydroxy group is present, it will important for the beta activity. If we remove the 4 hydroxy group and it will maintain only the third hydroxy group, then it becomes more alpha activity. And if we remove both the hydroxy groups, what happens? It will decrease both the activities, that is the alpha and beta receptor activity. So these are in short the SAR for the phenylethylamine. Now we will move to the SAR of adrenergic agents regarding the imidazole as a basic nucleus. Okay, so this is the general structure for the agonist drugs having the imidazole in their ring structure. So this is the imidazole ring. This is the X part, that is the bridging unit. It bridges between the aromatic moiety and the imidazole ring. So the total structure, it consists of three parts. One is the imidazole ring, second one is the bridge, that is the bridging unit which bridge between the aromatic part and the imidazole, and third one is the aromatic moiety. So we will start the SAR with the bridging unit, that is the X part, which is present in between the aromatic group and imidazole ring. So here you can observe X part is generally CH2, then the drug is alpha 1 agonist, and if it is NH or amine part, it shows the alpha 2 agonist activity. So in a drug, if you find the imidazole ring attached with the bridging unit, which is the CH2, then drug is definitely alpha 1 agonist. And if at the X part there is a NH, then the drug must be the alpha 2 agonist. Usually a single methylene ring is present in between aromatic part and imidazole ring. So here you can observe this CH2 group is present. So this CH2, that is the example oxametazole. So as per the SAR, if CH2 group is there, the drug becomes more alpha 1 agonist. Here you can observe amine group or amine part. So at that time, the drug becomes more alpha 2 agonist. So this clonidine is alpha 2 agonist. This oxymetazoline is the alpha 1 agonist. Now the imidazole ring. So imidazole ring is present, but if imidazole ring present in the form of open ring, so here you can observe the imidazole ring is made in the form of open chain. At that time, the drug is highly active against or highly active for the alpha 2 agonist. And third part, it is the aromatic ring. So the agonist activity can be increases if it is substituted like chlorine or small alkyl groups like methyl group. Generally they are placed in two ortho positions. दोन्ही ऑर्थो पोझिशनला हे ग्रुप प्रेझेंट असले पाहिजे, either two alkyl groups or the halogen groups. So they will enhance it agonist activity of a drug. So this is about the small part for the SAR of the adrenergic agents which have the imidazole meaning. Only what you have to understand, if it is CH2, it becomes alpha 1 agonist. If it is NH or amine, the drug becomes more alpha 2 agonist. Okay, now we will see some drugs comes under the adrenergic agents one by one. Now we now understand what is the SAR of the phenylethylamine and the imidazole. So if a structure of drug is there, so we can identify that is it is more alpha 1 agonist or alpha 2 agonist or beta 1 beta 2. So we can understand from the structure of a drug. Now for example, we will go for the basic neurotransmitter, that is naturally occurring neurotransmitter. So norepinephrine. So here you can observe in case of norepinephrine there is a hydrogen is present at that part. If the hydrogen is present, there is no any substitutions like alkyl substitutions. So what happens? Drug is more alpha agonist as compared to beta. Okay, here methyl is there, so drug is active against alpha as well as the beta. But here you can find out the drug is having bulkier alkyl group, that is they having the three alkyl groups. That means the drug is more active towards the beta receptor. And if it is tertiary butyl like in the cholesterol, so drug is more beta 2 selective agonist. So from the structure you can understand what is the activity or what is the specificity for the activation of that drug. If at the terminal amine only the small hydrogen is there, it is more alpha agonist as compared to the beta. If methyl group is there, so it is active against alpha as well as the beta. But it is having the higher alkanes. So here higher alkanes are there, so they are active against beta 1 and beta 2. But here this is the tertiary butyl, so it becomes the selective active against the beta 2 receptor. Here labetalol you can observe. So as per the SAR, after the amine, if there is a higher alkyls or bulkier groups is there, drug becomes antagonist. So labetalol is the alpha antagonist or anti-alpha adrenergic agent. Okay, so another example, alpha methyl norepinephrine. So what happens here? CH3 is present and here only hydrogen. So due to the hydrogen, it becomes alpha agonist, and due to the CH3, it becomes alpha 2. So it is selective for the alpha 2 agonist activity. Now in case of metaproterenol, so you can observe 3 dash and 5 dash. These are the two hydroxy groups as well as here the higher alkyl group. So it becomes beta receptor. इथं कुठेही तुम्हाला substitution आहे, so it is not alpha agonist. But these are the two 3 dash and 5 dash two hydroxy groups are there. So it becomes more selective agonist against the beta 2 receptor. Now here you can go for albuterol. What albuterol? They having the tertiary butyl as well as here CH2OH. So due to the CH2OH, it becomes more beta selective, but due to the presence of the tertiary butyl, it becomes beta 2 selective. So you can see the example of amphetamine. So there is absence of both the hydroxy groups. So when there is absence of both the hydroxy groups present, what happens? The drug becomes directly or indirectly acting. It is not selective for the alpha and beta, or the activity for alpha and beta becomes less as compared to the drugs which are in the hydroxy group at this position. Here we know in case of oxymetazoline due to the CH2 bridge, it becomes more alpha 1, and here clonidine due to the nitrogen bridge or amine bridge, it becomes more alpha 2 selective. Okay, guanbanes, it is more alpha 2 agonist as the open imidazole ring is present. So such kind of structure, by observing only the structure, you can find out the drug is more alpha 1 or alpha 2 or beta 1 or beta 2 selective, or which selectivity the drug has. So from observing the structure, it is easy for you to write down their selectivity. Now classification of sympathomimetic drugs. So these sympathomimetic drugs, they are classified into two types: directly acting, second one indirectly acting, third one mixed acting. In the directly acting, there are endogenous catecholamines, then alpha agonist, then dual alpha and beta agonist and beta agonist. That means the drug which act on alpha receptor, they are alpha agonists; which act on beta receptor, they are beta agonists. But which act on both alpha and beta, they becomes the alpha and beta agonist. And endogenous catecholamines, these are the drugs which are, these are actually not the drugs, these are the neurotransmitters which are secreted in our body, like epinephrine, norepinephrine. So this comes under the endogenous catecholamine agents. So indigenous catecholamine agents, you can observe there are three: dopamine, norepinephrine, and epinephrine. So dopamine, here you can observe the structure of dopamine. There is absence of hydroxy group is there. It causes vasoconstriction as the alpha 1 activity, and it increases heart rate. as a beta 1 receptor or activity on beta 1 receptor. So this is used in the treatment of shock. Second one, norepinephrine, you can observe there is only amine group is there. So in hypotensive crisis, the drug norepinephrine can be used. Then the epinephrine where it is CH3 is there, so it is more active towards beta 2, or it having the similar kind of activity against alpha as well as the beta. So it is useful in the treatment of hypotensive crisis as well as the nasal congestion as the alpha agonist activity. And we know uh, beta 2 activity, beta 2 causes the bronchodilation. So in case of asthma, the beta 2 drugs can be used. So similarly, epinephrine can be used in the treatment of asthma as a bronchodilator due to the activity on beta 2 receptor. Then second part, that is the alpha agonist activity or drug which having the alpha agonist activity. So due to the phenylethylamine, which is the basic nucleus, so phenylphyrine, methoxamine, midodrine, these are the drugs. Then due to the aryl imidazoline or imidazoline structure, this naphozoline, tetrahydrozoline, xylometazoline, oxymetazoline, these are the structure. Then 2-amido imidazoline, that is the clonidine, aproclonidine, brimidine, these are the structure. And the open ring imidazoline, what we have seen. So examples are guanbane and guanfacine. So these are the alpha agonist drug. They only act on alpha receptor. They are not acting on the beta receptor. So these are the drugs. So phenylethylamine मध्ये phenylphyrine आहे, अरिलिमिडाझोलिन मध्ये नॅफोझोलिन, टेट्राहायड्रोझोलिन, झॅलोमेटाझोलिन, oxymetazoline are there. In case of 2-aminoimidazoline, the drugs are clonidine is there. And in case of open ring, what we have seen, open ring, that is the guanbanes. So guanbanes and guanfacine, these are the two drugs which are the open ring imidazoline structure. So first, phenylethylamine. So all the phenylethylamines are alpha agonists. They generally lack the catechol moiety, that is, they are not metabolism by the catechol-methyltransferase. So when both the hydroxy groups are present, they undergo metabolism by catechol-methyltransferase. But due to the absence of this one, they only acts against alpha-1 agonists and they are not metabolized by catechol-methyltransferase. Hence, they having some kind of increase the duration of activity as compared to the drug which having the catechol nucleus. So example of drug, that is the phenylphyrine. So this is the structure. This is the structure of phenylphyrine. So it is generally served in the hypotension as well as the nasal decongestion, as it is alpha 1 agonist. It also used to dilate the pupils and it is used in the open angle glaucoma treatment. The next class, that is the 2-aryl imidazoline. So all drugs which are alpha agonists, they are generally used as the nasal decongestant as well as the ophthalmic decongestant. So the examples are, these are the 4 examples which comes under the 2-aryl imidazoline structure. Okay, so this is the drug naproxolone. So R is this part, that is the naproxolone. If that is this one, it becomes tetrahydrozoline. If it is this part, it becomes oxymetazoline. And if it is this part, the drug becomes xylometazoline. So all these structures are there or their syllabus for you as the alpha 1 agonist. So when imidazole ring is present, it having the pK value in between 9 to 10 and it is limited access to the CNS. And in between these two, you can observe only single carbon is there, or you can say CH2 group is there. It is the bridging unit. If you find bridging unit as the CH2 group, we know it becomes alpha 1 agonist. So all these drugs are alpha 1 agonist. If it is nitrogen, then it amine, it becomes alpha 2. But all these structures, they having the CH2 in their structure, so they becomes alpha 1 agonist rather than alpha 2 agonist. Then 2-aminoimidazoline here you can find out clonidine. Clonidine, it consists of amine group. So due to the amine group, it is more alpha 2 agonist activity as compared to the alpha 1 agonist activity. So it is as the muscle decongestant. It has the low PK value. So it remains non-ionized, so they can cross blood-brain barrier easily. So to cross the blood-brain barrier, the drug should be unionized form or in the lipophilic form. So due to the low PK value, this clonidine remains in the non-ionized form, and hence it can cross easily the blood-brain barrier. So it can produces the alpha 2 activity in the CNS. So it is useful for the hypertension or to maintain the hypertension. From nasal decongestant is also one use, and another is the hypertension, that is, it brings down the increased pressure to the normal. Then open ring imidazole, in that there are two examples. One is the guanfacine, second one is the guanfacine. The guanfacine, it having the PK value that is 8.1, so it is mainly becomes non-ionized, so it can penetrate central nervous system. Similarly, guanfacine also PK value 7, so it is also present in the non-ionized form, so it can also penetrate the central nervous system. So instead of imidazole ring, they are having the open chain imidazole in their structure. So just write down the structure of guanfacine. Nitrogen is there, or open chain, so it becomes the alpha 2 agonist as compared to the alpha 1 agonist drug. The next drug, that is the methyl dopa, which is the precursor for the dopamine. This is the structure of methyl dopa, that is methyl dopiate. That is the COOCA2H5, that is the ester form they have made. Due to the ester form, what happens? It increases the duration of activity. So when it enters, it undergo decarboxylation, so it undergo esterase or hydrolysis. So this breaks and it produces the drug, that is the L-alpha methyl dopa. So this L-alpha methyl dopa undergo decarboxylation by the enzymes dopamine decarboxylase, and it produces the alpha methyl dopamine. And then this alpha methyl dopamine, it is on hydroxylation, it converts into the alpha norepinephrine. Okay, so originally it is designed as the dopamine but decarboxylase inhibitor, but it is metabolized by the enzyme and give the active metabolite, that is the alpha methyl norepinephrine. And as it consists of CH2 group, CH3 group, so it becomes more selective for the alpha 2 agent. So it is used as the antihypertensive agent. The next part, that is the beta agonist part. Okay, so isoproterenol, that is the synthetic beta agonist, metaproterenol, terbutaline, they are generally utilized as the bronchodilators. Then albuterol, pyrbuterol, salmeterol, formoterol, bilateral ritodine. So all these drugs, they becomes the beta agonist. It is the isoproterenol to the ritodine. So these drugs comes under the beta agonist drug. Okay, so this is the structure of isoproterenol. Please write down the structure of isoproterenol. So you can observe it is the propyl ring. So it is beta agonist rather than the alpha agonist. Also, there is no any substitution at this position. It indicates the drug is more beta agonist as compared to the alpha agonist. Write down the structure of isoproterenol. The next drug, that is the bronchodilator, that is the metaproterenol. So here you can observe in case of metaproterenol there is a 3-5' hydroxy group, and when the hydroxy group is not in the 3-4' position, instead of that, if it is at the 3- and 5' position, the drug becomes more selective towards the beta agonist, that is the selective beta agonist. In case of terbutaline also this part is similar. In metaprotenolol this is R is the propyl part. In case of terbutaline this R is the tertiary butyl. So they becomes more selective towards the beta 2 receptor. And as we know that when the adrenergic agents they bind to the beta 2 receptor, they are responsible for the bronchodilation. That's why in case of bronchitic asthma, metaprotenolol, terbutaline drugs they are given for the bronchodilators to dilate the bronchi and to relieve from the bronchial asthma. Next drug that is the albuterol, pyrbuterol and salmeterol. So this is the general structure. If X is equal to C, R is equal to propyl, the drug becomes albuterol. In case of pyrbuterol, the X is nitrogen and R is the tertiary butyl group. Here is also the butyl ring. In case of salmeterol, the X is the carbon, and this is a long chain substitution in the form of R. Okay, so drug becomes generally more selective towards the beta 2 receptor. Write down the structure: albuterol, pyrbuterol, and salmeterol. Please write down the structure. So all these structures they having the CH2H group instead of the hydroxy part, that is the 3' hydroxymethyl moiety. So the drug becomes more active towards the beta 2 agonist. So all these three structures are more agonist towards the beta 2 receptor. Then due to the bulky substitution, here you can observe it becomes selective beta receptor. That's why these are the characters of the structure which is responsible to make them more selective towards the beta 2 receptor, and as well as due to this modification it is difficult for them to undergo metabolism by the catecholomethyl transferase, as well as due to the bulky R group they cannot be metabolized, or very rare amount they can be metabolized by the monoamine oxidase. So that metabolism can be reduced by modification in the structure, and that becomes more metabolism resistant, as well as they becomes more selective towards the beta 2 receptor. This is the structure of colterol. This is tertiary butyl, so they becomes beta 2 selective agent, as well as there is no any substitution on these alpha carbons. So such modifications in the structure, the drug becomes more selective towards the beta 2 receptor. Then butyl. This is the structure of butyl. Then ritodrine. Here you can observe this is the bulky group at this position. This is CH3, and this is only the hydroxy group. This hydroxy group is present at the fourth position. Due to the presence at the fourth position instead of third position, it becomes more beta 2 selective, and they are utilized as a uterine relaxant agent. Then next part of the sympathomimetic drug, that is the indirectly acting. So indirectly acting, there are three drugs, that is the amphetamine, methamphetamine, and hydroxyamphetamine. So these comes under the phenyl isopropylamine. And another class that is the phenylpropanolamine, that is the pseudoephedrine. So there are four drugs. One is class of phenyl isopropylamine, that is amphetamine, methamphetamine, and hydroxyamphetamine, and second one that is the phenylpropanolamine. As they divide off the catechol nucleus, they become the indirectly acting agents. Okay, you can see structure of amphetamine. So there is no hydroxy group, methamphetamine, no hydroxy group. Here there is a hydroxy group, but it lacks alpha hydroxy group. So here तिघांच्या structure मध्ये alpha hydroxy group आहे, as well as catechol nucleus is also not present in their structures. That's why they become, instead of alpha and beta selective, the drug becomes more indirectly acting symphotomimetic agents. So amphetamine and methamphetamine, they mimic the release of catecholamine, that is the norepinephrine and dopamine, as well as the serotonin. They produce a CNS stimulant and appetite suppression effect. While hydroxyamphetamine, they don't have any CNS activity, but due to the para-hydroxy positions, they are responsible to dilate the pupil. So in case of diagnosis or the surgical procedures on the eyes, such drug is utilized to dilate the pupils. The next indirectly acting, that is the phenylpropanolamine, that is a pseudoephedrine. So this ephedrine, we can find out RS configuration is present, it becomes negative ephedrine. If SR configuration is there, so इथे R असेल आणि इथं S असेल तर ephedrine, R असेल तर negative ephedrine. So RS configuration is there. So beta hydroxy having X S stereochemistry. At that time, there is no directly acting mechanism causes indirect vasoconstriction. So they act as the muscle decongestant. So epinephrine, it having the reciproc mixture, that is the RS configuration as well as the SR configuration. So they are diastereomers also. That is the RR and SS. These are called as the pseudoephedrine. SS configuration or RR configuration, these are the diastereomers of positive ephedrine and negative ephedrine. They are called as pseudoephedrine and negative pseudoephedrine. So they are having the indirectly acting drugs, and ephedrine, they are having the mixed acting drugs. These are the reciproc mixtures of, they are the enantiomers of each other. काल ephedrine मध्ये हा R आणि हा S असेल, it becomes plus ephedrine, and जर opposite configuration असेल, it becomes negative ephedrine. RS, it converts into the RR configuration, so drug becomes pseudoephedrine, that is the negative pseudoephedrine. And this SR, it becomes SS, the drug becomes pseudoephedrine, but that is the positive pseudoephedrine. So the when drug is in the ephedrine form, they are the mixed acting drugs, and when it becomes the pseudoephedrine, the drug becomes the indirectly acting. So this pseudoephedrine and ephedrine, they are the mixed acting drugs as well as indirectly acting drugs. Last one, mixed acting, that is the negative ephedrine. So that is the configuration, that is the 1R 2S D negative ephedrine is more active than all the four forms, that is the SR, RR, SS. These are the four other isomers, three other isomers, and this is the four, that is the RS isomers. Okay, so this RS isomer is more active, or the negative ephedrine is more active than positive ephedrine, than positive pseudoephedrine, than negative pseudoephedrine. So as a mix acting, it having the variety of activity, they can act as a bronchodilator, vasopressor, cardiac stimulant, as well as the drug can act as a muscle decongestant. So these are the different activities you can observe from the ephedrine. Okay, so in these methyl analogs of ephedrine, So here NCH3 is present. So when it undergo metabolism, this CH3 is removed and here hydrogen we are getting. So that is the NH2. So this is the this methyl analog of ephedrine. So it lacks N-methyl group. So they becomes more polar. So much less stimulation, they are becomes alpha selective and they having the higher vasopressin activity as compared to the ephedrine. Generally, they are used as the appetite suppressant, cough and cold medication. Now, still that this drug is discontinued from the use by the US FDA. Okay, so these are the points regarding the adrenergic agents, that is the agonists. So it includes symphytomimetic, which having the phenylethylamine structure, then imidazole as a structure. Okay, then there are different classification as we have seen. Endogenous alpha agonists, which act on both, which act only beta agonists, which having indirect agonists, which having the mixed acting agents. So all these classifications, it is of symphytomimetic drug. So due to the structural changes, the drug becomes more selective towards one of the receptor. Hence, the structure is more important or the SAR is more important for the adrenergic agents. So there is a compulsory question asked regarding the SAR of adrenergic agents. Now, after agonist or adrenergic agents, we are going to the next part, is the symphytolytic agents. So the agents which can block alpha receptor or beta receptor, which can block the activity of this receptor. These agents are called as adrenergic antagonists, or they are also called as symphytolytic drugs. So they are having the opposite activity to the agonist drugs. Okay, so these antagonists, they are classified into alpha. In case of alpha 1, alpha 2 blocker, in case of beta blocker, they are classified into beta 1 blocker, beta 2 blocker, beta 3 blocker. So such drugs, they are also called as adrenergic antagonist agents, or they are also called as symphytolytic agents. So what is the therapeutic uses of alpha blocker? So in treatment of hypertension, alpha blocker can be used. So generally alpha blocker, they are used to treat the high blood pressure, and generally used with the combination with the agents like diuretics when we have to decrease the increased pressure, that is for the treatment of hypertension. They are also responsible for the vasoconstriction, BPH, Raynaud disease, phenochromia, phenochromocystoma, CHF, erectile dysfunction. So for the treatment of all these parts or all these diseases, we can use the alpha blockers. So regarding the blockers, as we know, this drug can block the receptor if they have the structural similarities with the concerned neurotransmitter. If such similarities is present, then drug can block the that receptor. Suppose the drug having the structural similarities with the adrenaline, then only the drug can bind to the receptor and they can block the receptor. If they having very different or variety of structure as compared to the adrenaline, it is difficult for the drug to bind to the receptor and block the receptor completely. Hence, for a drug to act as an antagonist, it must having some kind of similarities with the drug which act as the neurotransmitter or the neurotransmitter which binds to that receptor. So in case of beta receptor antagonists, they having the similar kind of structure with respect to the agonist norepinephrine, epinephrine as well as the isoproterenol. In case of alpha antagonist, they having a diversified structure but little resembles with the alpha agonist structure. But generally they having a diversified structure. So there is no such kind of similarities which is present in case of alpha antagonist. So write down the structure of alpha blockers: phenoxybenzamine, tolazoline, phentolamine, rosocin, doxazosine. Please write down the structures. Write down the structure of phenoxybenzamine. This phenoxybenzamine is the irreversible alpha blocker. That means once it blocks the alpha receptor, it will not again free that receptor. So permanently it blocks the alpha receptor. So it called as the irreversible alpha blocker. So phenoxybenzamine as the example. Please note down the structure. Then non-selective alpha receptor blockers. In that the drugs are tolozine and phentolamine. So these are the examples which are comes under the non-selective alpha receptor blocker. The both drugs are competitive. They are active against both, that is the alpha 1 as well as the alpha 2 receptor. So they block alpha receptor as well as the alpha 2 receptor. Write down the structure. Tolazoline and phentermine, which are the non-selective. Now we move to the next part, that is the selective alpha 1 antagonist. They having the quinazoline in their structure. Examples of prozosine, doxazosine, terazosine. So these are the examples which comes under the alpha 1 antagonist. Write down the structure of prozosine and doxazosine. If this R is this one, it becomes prozosine. If this is the structure in this form, the drug becomes doxazosine. Okay, please write down the structure. Prozosine, doxazosine. Okay, so today we have seen the SAR of imidazoline structure. So if carbon is present, it shows alpha 1 receptor. If nitrogen is present, it shows the alpha 2 receptor. So that is the structure of these alpha 1 and alpha 2 receptor in form of imidazoline we have seen. Then we have seen the classification of symphytomimetics along with the examples of drug which drugs contains and what is the structure of that drug and how the structure affects the its therapeutic activity of a drug after the having their different structures. And then we have seen the irreversible alpha blocker, non-selective alpha receptor blocker, and selective alpha antagonist. Okay, detail regarding this we will see in the next lecture. Okay, we will stop here.